So welcome to the September CLF Vancouver webinar. Today we are here with Ivan Lee, Navid, Hossaini, and Patrick Enright, and we're going to be talking about the Embodied Carbon PathFinder Tool and costing study. So today we have also managed to get AIBC credit approval for anyone who is an AIBC member, and we'll drop a couple of links into the chat in the next few minutes if anybody would like to register for that. And then this webinar will actually be recorded, so you should have got a pop for that already. But we do just ask that everybody keeps themselves on mute and with their cameras off until we have the Q&A at the end, when feel free to turn your cameras back on and join in the discussion. But for the main presentation, we'll just have the speakers with the cameras on. And then lastly, before I hand it over to our speakers, I would like to acknowledge that we are grateful and privileged to work on the unceded and traditional lands of the Musqueam, Squamish, and Tsleil-Waututh peoples. And with that, I'll hand it over to Ivan.
All right, thanks, Carolyn. Let me just share my screen here, get set up. Okay. Okay, here we go. So yeah, I'm going to start off with a brief background and introduction to the Embodied Carbon PathFinder tool. My name is Ivan Lee. I'm a building science consultant with Morrison Hershfield. I've been with the company about 12 years now. For those of you who may or may not be aware, but Morrison Hershfield is a engineering consulting firm, mostly focused on civil. We're multidisciplinary. We do everything from environmental services to transportation, building bridges, traffic design, as well as buildings. And buildings is within the realm that I work in. Most of my experience has been on the modeling side, particularly for thermal modeling for thermal bridges, as well as hydrothermal for durability. But as you know, most of the industry, we've also kind of shifted focus on to kind of reducing our carbon emissions and carbon pollutions, and that kind of brought me into doing some LCA work and that type of stuff. Funnily enough, Morrison Hershfield actually is no stranger to embodied carbon, despite that it's there's renewed interest in this realm. We've actually had partnered up with the Athena Institute back in 2010 to help them develop the first impact estimator. So this is something that's definitely been up our alley for a while. So we'll start off with a brief background on what the Building PathFinder tool is. And some of you may or may not be familiar with it, but we'll kind of describe how it is different than the operational tool that most people have seen. We'll then get into some more specifics of the LCA models that we've created, talk about some of the scopes, the model boundaries and assumptions, and then we'll go into a brief description of the archetype buildings that are within the tool itself, talking about the parameters as well as some of the characteristics so that you can have a bit more background and better understanding of what the buildings are. And then we'll go into a really quick demo showing you around the tool and how to move around it and get some information. So a bit of background on the tool itself. The Embodied Carbon PathFinder tool was actually a spin-off of another project. Just before the pandemic, the city of Vancouver got us to, we were involved with the city of Vancouver in doing an embodied carbon reduction study. And this study was to help support them in their work in developing embodied carbon policy, which Patrick later on today will talk about. And to do that, we basically wanted to investigate different impacts of low carbon or low embodied carbon design strategies. And one way to do that was to create a huge swath of data and analyze their impacts. So we turned to parametric analysis for this. And once we've created that whole set of data, we thought that it would be beneficial for the industry as a whole if we were able to release it, and hence the creation of this tool. So here's basically the project team that were involved in development of this tool. We have the Athena Institute, who provided us with guidance and and some technical support in terms of our LCA models, as well as running their impact estimator tool. City of Vancouver, who also supported us not only fiscally, but also provided some information and background and feedback into our tool development, as well as our development of our archetype buildings as well. And then we've got Open Technologies, who are hosting this, or have created the website and are hosting it on their servers. And finally, Morrison Hershfield, we are the ones, the consultants who kind of did some of the legwork that crunched the numbers to create this data set. And I'd like to mention that I'm only one part of the team here at MH that was involved in this tool. There are two others. There's also Mark Lusick and Callum Galley. I just happened to be the one who drew the short straw to have to present today. But without them, the tool would not basically exist. So here's what the tool generally looks like. And this is maybe familiar to you if you have seen it before, have used it before. But the Building PathFinder tool, for those who are not familiar, is basically a visualization and interactive tool that allows people to figure out relationships between different parameters within a building. So this is really well set up for presenting parametric data and figuring out relationships between multivariate solutions. So in this case, I've screenshotted the operational energy tool. And basically each one of these lines here represents an energy model. So basically there are multiple models out here and multiple cases of data and scenarios. This kind of beats out having published a whole set of Excel sortable data that's going to be a little bit more boring and a little bit less flashy. Here we've got, nice colors, and it's interactive, and you can filter out through the different parameters in here to kind of get narrowed down to your solution. And I'll get into kind of how the tool works later on. But to dig into this a little bit further, contrasting between the operational energy pathfinder and embodied carbon pathfinder, the operational energy one provides 3 different metrics, kind of 3 results at the end. And the outputs are mostly TEDI, the total energy density, the thermal energy demand intensity, TUI, the total energy utilization density, as well as GHGI, greenhouse gas emission intensity. And they're all, all the units are per, floor area per year. Whereas for the embodied carbon pathfinder, there's really only one output, and that's GWP, or global warming potential. And that's basically the amount of carbon that's emitted in basically the life cycle of the building. One thing to note is that while the two of them are similar and they share there's some overlap between some of the archetype buildings, they're not equivalent. So as yet, you cannot do a whole life carbon study based off of the Pathfinder tool itself. It's not to say that you can't do it in the future, but for now, with the data that's currently on the website, you can't do it. The 2 archetype buildings are not the same. So as I mentioned before, we had to do a parametric analysis to figure out, to kind of present this data. So the tool itself has about over 700,000 LCA models for 3 different archetype buildings. We considered various options and different combinations of materials. So we had variable materials for structure, for the building envelope, including things like walls, insulation, windows, and roofing. We didn't just throw all the different variations into the tool and let it and kind of sort itself. We actually tried to be smart and filter out scenarios that would never be built. Either it violates building code, or it has really poor durability performance. So for example, you won't get a scenario where you've got wood columns supporting concrete floors, because you'd be supporting something, you would have basically combustible components supporting other non-combustible components. And likewise, you wouldn't get fiberglass insulation in spandrel assemblies, because we know, like, basically in spandrel back pans, they're going to get wet at some point, and fiberglass really performs poorly when it gets wet. So we try to be careful with throwing a bunch of data in there. Now, some of you may be thinking, why create another tool? What's the point? Is this, is this going to be another tool that I have to learn and use? Well, yes and no. We think this tool has a unique place within the industry and within the library of this whole suite of tools that are available right now. The Embodied Carbon PathFinder is really good for evaluating designs or doing comparative analysis early on in your design stage, when you have more questions than details figured out yet. So you may want to, so questions that you would consider would be, well, what if I used, like obviously we know in terms of structure, if we went from concrete to mass timber, we know there's going to be huge reductions, but what about something in between, concrete and steel? How would that look? And so it's really good when you don't have a lot of details within your design to help figure out what are the overall impacts, what are the big ticket items for each archetype, and so that helps you narrow down into what you should be focusing on as you progress into your design process. And we envision that for most projects, as you move on, you would have to eventually do a whole LCA model, a whole building LCA model that would capture some of the details that aren't captured within the Embodied Carbon PathFinder tool. So a little bit about the scope in terms of the LCAs. The LCAs that are in the tool right now only include the main structure, the building envelope, as well as the parking structure. It does not include things like interior partitions because there's just too many variations in terms of partitions, so that was left out. And the whole and mechanical, electrical, plumbing systems as well. That's a little bit of still a gray area within the industry, and we decided not to complicate things by including it in there. As far as the scope goes, we've included everything in all the stages in the product stage as well as construction stage. So that would be going things from A1 to A5. We included stages B1 to B4 in the use stage, as well as end of life stage, so C1 to C4. We did not include material reuse and those things as well, because we also wanted to keep things simple as much as possible. As far as the LCA models themselves, they were all developed with the Athena impact estimator. So with that, we made use of some of their GWP data that are already built in, but then we also supplemented it with different EPD data. So even though we used Athena models, we did not pull models or values straight out of the models. We actually had to make some adjustments to kind of align it with what we see in terms of construction that's currently outside or in the field. So one of the things that we had to modify was the column sizes. Within Athena, it has structural design assumptions in there, so it will adjust some of the structure. But one of the things that we found in looking at archetype buildings or different various buildings across the city, as far as the ones that we've also worked on, is that column sizes for high rises tend to get bigger as you move down to the lower floors, because you're carrying the extra load above you. But Athena was not doing such a good job of characterizing that. So we actually had to adjust this column size manually, but just adding more concrete into our models. Similarly, for load-bearing wood frame walls, we also had to add in extra framing in there as well. Because if you were to use the assumptions based in Athena for wood frame walls, even load-bearing wood frame walls, the people that were developing it did not envision that we would be building 6-story wood frame buildings at all. So we had to kind of beef up some of that. And then one of the common components that we build here in Vancouver would be window walls, but window walls cannot be found directly within the Athena impact estimator, and there wasn't a lot of data available in terms of EPDs for window walls. So what we had to do was compare kind of materials between a typical curtain wall with a window wall, figure out the differences in quantities and material quantities, and then adjust to that and kind of add that into our model. Other assumptions for concrete, we just assumed, we tried to keep things simple, and we just assumed that the base concrete strength would be 35 MPa. The only thing we adjusted were the SCM contents. So we went all the way from 0 to 40. For insulation, we kind of diverted away and avoided using some of the values that are in the impact estimator. Instead, we looked at EPDs because we know the whole insulation industry is changing and we want to be up to date. So we use both industry-wide and product-specific data. We included data from 2018 as well as 2020 or 2021 for foam products partially because as part of the City of Vancouver study, they wanted us to kind of baseline things back to 2018 construction. So we left that data in there, but we also know that with the new regulations outlawing certain fill gases, is the GWP for those same products have gone down significantly. So we included both versions of insulation in there. For the high-rise building, the amount of insulation that we put into our models was everything was kind of normalized to R15. So we just adjusted the thicknesses so they achieve a nominal R15 in the walls. But for the mid-rise and low-rise archetype for the other two, we just stuck with everything at 4 inches. I think at the end, it doesn't really matter too much because we're not trying to look at operational carbon and embodied carbon at the same time. We just wanted something that was representative. And for high-rise buildings, the amount of insulation generally is about the same, but the types kind of vary. So rather than varying the thicknesses, we decided to go with the nominal insulation value itself. Whereas for some of the smaller buildings, the thicknesses, there seems to be more uniformity within the thicknesses rather than the level of insulation, even within different insulation types. So that's why we chose that. So here's are the 3 archetypes. We have a high-rise residential, a mid-rise residential, and a low-rise residential, which is represented by a stacked townhome. These archetypes were developed with the help of City of Vancouver. They had sent us drawings from recent building permit applications back, around 2020. We also supplemented that information with some of the buildings that we've worked on as well and made our own adjustments. So these are buildings that are representative of what you would typically find within the city. And we try to get that as close as we can. So some of the characteristics of at least for the high rise, we set it to 30 stories, a floor plate of 25 meters by 25 meters. So it's fairly compact. The lifespan is around 60 years, so similar to most LCAs. As far as the structure, we set the live load at 2.4 kPa, 8 meters beam span, and this is really more for Athena than anything else. Our foundations, we've got about 100 millimeters or 4 inches of concrete slab on grade. The below grade walls are about 200 millimeters or 8 inches thick. And we've got footings that are about 300 millimeters by 100 millimeters or a foot by 4 inches along the perimeter walls as well as below the columns. And you'll find that for most of the foundation stuff, it's pretty standard across the three archetype buildings, trying to keep things simple. So as far as some of the parameters that we considered for the high-rise building, we looked at both cast-in-place concrete and mass timber for the structure. For the walls, we considered window wall, curtain wall, steel stud infill, precast sandwich panels, as well as CLT. We also looked at parking in the form of below grade parking for up to 2 to 6 levels, going into increments of 2. And for the roof, we just selected kind of typical flat roof design. So roof membranes of EPDM, SPS, or PVC. Insulation, we looked at mineral wool, spray foam, polyiso, and XPS. In the cladding, it's meant to be pretty standard, glass, metal panel, brick, that type of thing. Window wall ratio, we looked at 40 to 60%, both double and triple glaze, and basically aluminum framing, either punch windows or integrated within the assemblies, like the window wall, curtain wall. For the mid-rise, it's also 6 stories as well, or it's set to 6 stories. The floor plate is about 75 to 25 meters, so it's a little bit more longer. Everything else is about the same. The joist spans or the beam and joist spans were a little bit different. This is to accommodate some of the things in Athena, but everything else as far as the foundation is about the same. In this case, for the mid-rise, we actually considered more variables in there because we see a larger range of variability in terms of our mid-rise construction here in Vancouver. So we looked at concrete, steel, mass timber, as well as wood frame for the structure. For the exterior walls, we looked at window wall, once again, steel stud infill, but also wood stud infill, ICFs and CLTs. Parking was a little bit reduced. We looked at both street parking and parkade. And for the street parking, we don't count any of the GWP values within our LCA models. We kind of declare that as outside of our scope. For roofing, it's about the same. It's another kind of flat roof type of construction. Insulation, mostly the same as well, but we've also introduced looking into fiberglass bat as well as cellulose insulation. Those work really well with wood framing that we typically see. And then for cladding, mostly the same materials, but we also included fiberboard and eaves as well as PVC. Some of the common materials that you would see in a smaller building as opposed to a high rise. And for windows, it's kind of keeping with the same theme, 40 to 60% window wall ratio, double and triple glaze, but punch windows that are either aluminum frame, fiberglass, or vinyl. And the last archetype is the stacked townhome low rise. It's 3 stories, floor plate about 12 meters by 6 meters. Once again, most of the structure is still the same. And as far as the different materials or different parameters goes, we've got mass timber and wood frame. It's definitely a lot more simplified because there's less variability that we've seen in kind of low-rise construction. Walls, we've looked at steel stud, wood stud, ICFs, CLT. Parking, we just limited just to street parking. Roofs are also flat roofs. And insulation, we've got fiberglass bats and cellulose, so similar to the mid-rise. Cladding, again, very similar to the mid-rise as well. But for the windows, we kind of set the window wall ratio to something that's a lot lower, 10 to 25%, double glazed, triple glazed, and we looked at aluminum, fiberglass, and vinyl frames. So now I'll switch over to a demo of the website, so kind of give a quick overview of what it looks like. So when you go onto the Building PathFinder page, you'll see this, and you can see that now they've created it so that you've got operational energy on one side and embodied carbon on the other side. And these are all the various archetypes that have been modeled in here. And you can see that for the most part, they are a little bit different, but up here, they both have, there's 2 high rises. And this goes back to the first point I was that I mentioned, that these are not the same high rises. So don't get confused that you're thinking that, oh, it's because they're labeled the same thing, that they're exactly the same, but they are actually different. So when you select one of these buildings, it takes a while to load, but all the data and all the different cases are being loaded. Here you can get when you click on the Getting Start button, it gives you a brief background on how to use the tool as well as the methodology. So basically what I was kind of going through and presented in the presentation. So you find out a lot of the same information in there. We also have an FAQ. So it kind of goes into tries to answer some of the more common questions that would come up. So like, how are the archetypes determined? What are limitations? What is GWP? That type of stuff. And here, normally you'd be able to change regions, but right now all the data that's available is only for Vancouver. Here you can switch different building types. So we'll just leave it as high rise for now. You can also change the coloring style depending on which parameter you want to color it by, as well as the coloring scheme in general. And over here, this is kind of the main interface. So each of these lines, as I mentioned before, are each LCA model cases. And down here, it's just kind of a table that kind of lays out the specific information about those. And as we kind of go across here, these are all the different parameters or different categories. for the LCA model, and these are the parameters I get to select. So there's multiple ways of using this tool. You could, if you have a kind of a design in mind and want to explore certain parameters, it's also really good for that. So if we start off that way, let's say we have a concrete building, basically a typical building that would be a typical high-rise multi-unit residential building that we would build in Vancouver, but I want to look at some of the impacts. This is one way of doing it. So I'm going to select kind of the more simple and typical materials. And the way to find things is just to kind of scrub over them and select them. So it's relatively intuitive. So let's say I want to look at window wall ratio and how does that affect things. Well, if I keep scrubbing things here and there, I can now narrow down from all those cases down to basically 2. And here you can see when I mouse over the results, it highlights the line. So I can also sort them as well. So if I want something lower, basically it's telling me that if I were to increase my window wall ratio, I would actually get a lower GWP number. Whereas if I went to a lower window wall ratio, it would get higher. And that kind of makes sense because in this case, there's more embodied carbon within the window wall system than it would be in a double glazed or triple glazed window. You can also, if I reset everything back, you can also go at it from the other way. You can look at it from kind of the results and it kind of filter things out from there. So if I want to look on the lower end of my results, I can first filter this and then figure out what my options are. So kind of interesting enough, it did say you can still build with concrete out of to get a low GWP number. So let's just find out what that really looks like. So here, because I've narrowed it down to this, I can actually filter out all the other cases. That's by hitting this keep selection. And so that kind of helps me zoom in exactly to what's going on here. And if I really wanted to, I can also sort it through again and now look at, in this case, if I do want the lowest GWP value with a concrete structure, it's telling me that the case that would work is if I had sandwich panel walls with a steel floor, and within the sandwich panel, I'm using mineral wool instead of a foam insulation. I should be using polyiso PVC for the roof, as well as double glazed aluminum framing for punch windows, and 60% window ratio, 2 levels of parking, and 40% SCMs. So yeah, that's basically it in a nutshell. So I'll pass this over to Navid, he'll share more experience from the kind of user perspective.
Great, thanks Ivan for the introduction to the tool. My name is Navid Hossaini, and I'm the principal and CEO here at Recolletive Consulting. We are a B Corp certified green building consulting firm here based in Vancouver. We've been doing sustainability consulting for the past 16 years, and we have worked on a range of buildings, everything from single family homes to master planning of big projects such as Olympic Village. And we have, like, recently we've been focusing mostly on high performance buildings such as passive house projects, health and wellness consulting, and also embodied carbon is something that is very close to our heart. And so we've been focusing on embodied carbon for different projects and looking at net zero buildings and how we can help our projects reduce their footprint, not only on the operational side, but also on the embodied carbon footprint. So the purpose of my presentation is just to build on the foundation that Ivan built. So going through some examples of the tools that we have used the Embodied Carbon PathFinder for, and share some of the lessons learned from those tools and talk about some of the strengths and limitations of the tool from my perspective. So as Ivan mentioned, if you look at the full project life cycle of any construction project, starting from project planning stage to concept design, design development, construction documents, and detailed design and into construction. As the project gets more detailed and you have more specific information about the project, then PathFinder tool becomes less and less viable for your project. It's most powerful at that earliest stages of the project, everything from when you have an idea of the building that, yeah, we want to be building this building here, and we have just a concept of design at mind, or we know what we want to be achieving, and do you want to do a carbon budget for your project and figure out what is the embodied carbon footprint of your design. That's where PathFinder is most useful, and it does a good job in terms of scenario analysis. So if you're at that earlier stage, you're looking at different design options, as Ivan mentioned, if you're considering between double pane or triple pane glazing, or different insulation materials, or whether you go with low carbon concrete with STMs, or you want to stick with a regular concrete mixes, then it gives you an idea on what is the contribution of each of those factors and how you can reduce your footprint. Just want to mention that, like other whole building lifecycle assessment tools that you see some of them on the screen, like Tally, Impact Estimator, and OneClick, can also be used at those earlier stages. So there's an overlap at that earlier stage of the planning, concept design, and into, like, I would say halfway through the design development. But the advantage of PathFinder is that it's easier, it's quicker, and can be modified easily. So think of it as a Class D costing study. So it's useful to give you some information about the cost of your project, but you're never going to use that for your tender or for as a cost estimate for building your project. Just an idea that can help you at the beginning of the project to make some meaningful decisions. But not to mention that's the, like, even though it cannot be used for detailed analysis and can't give you the exact number of what is the footprint, the embodied carbon footprint of your building, but that is a very powerful stage, that planning stage, early design stage, that can lead to the highest carbon impact reduction. So this is a graph from taken from World Green Building Council. So on the x-axis, you see different stages of project, everything from planning to design, construction, and operation maintenance. And the y-axis, you see the carbon reduction potential. So as you go from left to right, your ability to reduce carbon reduces. So like the highest potential for reducing carbon is at that earliest stage that you're evaluating making those bigger decisions, whether you're going to be, what is your structural system and you're going to be using, whether you're going to go with double pane or triple pane, and how many levels of parquet you have, what is the building orientation and shape, and all of those things. So that's a very powerful stage that this tool can be useful, even though it cannot produce very precise results, but it can help you navigate different options and help you reduce your embodied carbon footprint for the project. So we use PathFinder, as I mentioned, on some project at the earliest stage. So I'm just going to go over a couple of projects that we used the tool for recently, and talk about some of the like how we use the tool and what was the decision that was made using the tool. The project number one, and again, I'm analyzing the projects, is a mixed-use development in North Vancouver, 4 mid-rise buildings with retail at grade. That the project is at the concept design stage. So the owner has the architect on board, and there are no other team members. So we don't have energy modeler on board to talk, or envelope consultant on board to tell us what is the insulation of the building, or what is the wall system, or a mechanical consultant to tell us what is the HVAC system, and so on. So we have limited information about the project, but the architect and the owner are keen to know what is the embodied carbon footprint of the building and how he can reduce that. So this is a prime example where PathFinder can be very powerful. So we use PathFinder, and as Ivan mentioned, we opened the tool, we had a session with them, looked at different options, tried to select different parameters for each of the areas that would impact the building, everything from the structural system, whether it's concrete or wood, all the way to levels of parquet and SCMs. And also we were looking at what would it take to get to certain targets. So this project is considering zero carbon design standard of CAGBC. So we know that under version 3, the new version, there is a minimum to hit. So the minimum 500 kilograms of CO2, that's the bare minimum that you have to hit. And you would also get innovation points if your design meets certain thresholds. So we were able to talk to them about different options and what would it take to hit the targets, and with an understanding that these numbers are not very precise. So as the design gets more advanced and we have more details about the different parameters of the building, we have to do a whole building lifecycle assessment using one of the more sophisticated tools to model the building. But at this earlier stage, it helped us to know that the designs that they were considering was in the ballpark of 275 to 335 kilograms of CO2 per meter square. So we are far below the 500 that is the threshold for zero carbon standard. So we with a high degree of confidence, we could have told them that, yeah, it is very likely that you meet that minimum. But if you want to go for the innovation points, which the threshold is around 340, then you have to be looking at more detailed design. The second project that we used the tool for was a multi-unit residential building here in Vancouver. And again, like the project is at the very early stage of rezoning inquiry stage. So, but we had a bit more information on this project. We had the architect on board, the envelope consultant on board, mechanical engineer on board. So we did have more information about the project and better understanding of the design. So what we did with the tool, we looked at 4 different design cases for the project, and mostly some of the parameters were fixed. We knew about them, but then the architect and the owner were keen on knowing what would be the impact of different cladding materials, and also what would be the impact of changing the window frame. So whether you're looking at window wall or curtain wall, what would be the impact? And so we use the tool, fix all of the other parameters and change those 2 parametrics and compare the results. And as you can see, the results range from 300 to 324. So again, the main thing to keep in mind here is that what this figure tells us is that which design is better than the other, and we shouldn't be fixated too much on these numbers because these could change as we do more detailed design. But we can say that metal cladding with curtain wall would perform better than glass building with window wall, basically. So just to talk about some of the strengths and limitations of the tool, as I mentioned, it's very quick, it's easy to use, and Ivan showed us how to use the tool, and that's it about it. Like it's very, very, very intuitive, and there is a good FAQ section that you can look into. And the other advantages are that it's free, it's web-based, so you could use it from your devices, your phone, and it's some of the other tools. The limitations are that they only work on certain operating systems, and like Mac user may not be able to use them. We don't have that issue here for Pathfinder. And as I mentioned, it's suitable for earlier stage embodied carbon analysis and is a powerful tool for scenario analysis, not only at the earlier stage, but as you design progresses, even if you're at the detailed design or getting into construction and you want to do quick analysis to see different cladding materials or different options, like how do they perform and which one is better, this is a quick and easy check for you. Some of the limitations that Ivan also touched on, there's limited number of archetypes right now. The entire focus is on residential buildings and 3 archetypes of residential projects. So if you have a building that doesn't fit into that archetypes, you may not be able to use the tool for different options for each parameter. So like there are so many different options for cladding or for different levels of parquet that you can have, but again, like the tool is kind of limited on the number of these choices that you have. And it looks at typical shape and massing. So if you have like a custom, a little bit regular design of the shaping and massing, then it might not be a very suitable tool. And as Patrick would emphasize on his part, cannot be used for compliance modeling. So if you're using the tool for City of Vancouver rezoning or LEED or zero carbon standard, it would be a powerful tool to guide you in the design and help you reduce your impact. But as you get to that compliance modeling and for submission to those entities, then you would need to use some of those other LCA tools. And with that, I pass it over to Patrick.
Thanks, Embiid. And thanks everyone for the chance to present to you today. I'm going to go ahead and share my screen here. Can everyone hear me okay and see that?
Yeah, it's great. Thank you.
Wonderful. Thank you. So I just, yes, want to acknowledge that we're coming to you on behalf of the City of Vancouver, which is on the traditional unceded territory of the Musqueam, Squamish, and Tsleil-Waututh people. And I think embodied carbon can have a lot to say about how we relate to the land and how we understand where materials come from and where they go, and where those you know, the ecosystems and the impacts that those materials have are important to how we relate to the land that we are privileged to be on. So I just wanted to acknowledge that and say a little bit about how I see embodied carbon relating to materiality and to reconciliation. But the main focus of my presentation today, Ivan and Navid covered the tool quite well, I think, and gave a great introduction to the PathFinder tool. We helped support the development of the PathFinder tool, and we also, it was part of a larger, some of that data generation was part of a larger study where we wanted to look at options to reduce embodied carbon, but also the costs. And so I'm going to share with you, I'm first just going to give a quick reminder of some of the context and the code changes that we've recently approved on embodied carbon. So what is the policy context that we're in here, and what is the reason that we're talking about some of these important topics today? And then I'll also share just a teaser of some of the results in that report, which will be available shortly on our webpage. So just a quick reminder of the policy context that we're working in here. Just making sure I'm keeping track of my time. So of course, Vancouver in 2019 declared a climate emergency. City Council declared a climate emergency, and we have a climate emergency action plan that is our plan to get us on track and to be consistent with the IPCC's 1.5 degree scenarios to keep climate change and global warming within 1.5 degrees, which is the safe limit for climate change. And that requires up to a 5-fold increase in the rate of reductions of emissions in the city of Vancouver by 2030. And then by 2050, we have to keep reducing until we hit carbon neutral. And then under those 1.5 degree scenarios, it's always good to keep in mind, we actually have to go negative after that. So reductions are great, more reductions are better. Getting to carbon neutral is important, but we actually also have to understand what it is to go beyond that as well. That has implications for embodied carbon. That has implications for how cities are beginning to understand what negative emissions mean, what natural climate solutions are. And this has fed into our, all of this has fed into our climate emergency action plan, which has 6 big moves. I'll be especially talking about, or focusing on Big Move 5, and all of this falls under our Big Move 5, which is our target to reduce embodied carbon as in the carbon from materials and construction practices, by 40% by 2030. But we have the other moves based around transportation, building emissions, and that last one, restored coasts and forests, is partly how we understand what those negative emissions could look like in the future at the municipal level, as well as how it ties into nature-based solutions. And that can have some tie-ins with embodied carbon as well. As I said, our goal is 40% by 2030. To do that, we created the embodied carbon strategy. And that vision actually goes beyond just a 40% reduction to what we call a healthy, equitable, circular, carbon positive construction economy. And the thing I want to highlight here is that there are many different areas of focus and action that need to come together to achieve that long-term vision. And I think there's a role for everyone in the industry to contribute to one or more of these different elements in achieving that vision. Our first major step in achieving our 40% reduction targets is just in May of 2022, this last year. Council approved changes to the Vancouver building bylaw, our building code, for 2023 and 2025. In 2023, we will require embodied carbon reporting in all Part 3 buildings. And this will be compared to a baseline that we'll be establishing as part of upcoming embodied carbon guidelines. So this is to begin to understand embodied carbon and to begin to be familiar with the processes of understanding and reducing embodied carbon for all large buildings in code as a matter of standard practice. We're also introducing for the first time a limit that says you can't be more than 2 times that baseline. And that probably won't affect any projects. And if it does affect any projects, it'll be very easy to achieve, but beginning to introduce that concept of a limit on embodied carbon. Moving ahead to January 2025, we're requiring 10 or 20% reductions, depending on building types and materials you can build out of, as well as at least one responsible material sourcing option. So that's just part of the context. We're trying to reduce embodied carbon in Vancouver. There are actually code changes coming up that will require those reductions as we look ahead to 2025. So what do these costs, what do the cost implications look like that, for reducing embodied carbon? I want to share with you some of the results that came out of this study that was went together with the Pathfinder creation of the PathFinder tool and the data that underlies it. But I also just want to start with a quick disclaimer, just that, you know, costing studies have many assumptions and market prices are always changing, but they can still give us a sense of what options cost in relation to each other, which tends to change less quickly. But even then, in some cases, I'll give some more caveats of our most up-to-date understanding of costs. And I also just want to quickly highlight, just so we're all on the same page, where embodied carbon is coming from. So this is from an Athena benchmark study a few years ago, but the truths are generally consistent with today's understanding, in that the vast majority of embodied carbon tends to come from the product stage, the manufacturing and the extraction of materials and manufacturing of building products and materials. The other stages, there are variations, and the other stages still have important embodied carbon implications, but the bulk are coming from that product stage. And then when we look at materials, the bulk are coming from concrete and steel as the most carbon intensive and most widely used materials. That can vary a lot, but just keeping in mind, if we're going to focus and keep our eye on where embodied carbon is showing up most, these are important considerations. And that is reflected in some of the results that I'll share. Before we get to the cost, I just wanted to quickly show, and I'm going to be focusing on the high-rise scenarios. I think that's where the most interest is, and sometimes the fewest options to reduce embodied carbon. We tend to build high-rises out of concrete and reinforced steel. So there's the fewest options there typically, but we did, as Ivan shared, look at both the high-rise and the mid-rise, as well as the townhouse archetypes. But just for the sake of time, I'm going to focus on the high-rise results. So those showed a range of reductions and a range of different outcomes. And mapped here are the percentage reductions from an approximate baseline that we defined as part of the study. Mass timber construction here is actually, we didn't cost mass timber because there's actually other whole studies dedicated to the costing of mass timber, and the cost is quite fluid among many things in the recent construction economy. But we understand that there's significant reductions potentially from mass timber, depending on whether you can build entirely out of mass timber or hybrid or what. But I think the thing I wanted to highlight here is that given that we're proposing 10% as a minimum requirement for buildings over 7 stories, there are still many, many options in this study, at least, to reduce embodied carbon at or beyond that 10%, even before getting into mass timber and other kind of structural material. So just looking here at the high-rise, the structural changes that were studied. The blue is the change in embodied carbon. So percent negative is good, and the green is the change in costs. So again, negative is good. And in some cases, with some caveats, there's potential to reduce both embodied carbon and costs at the same time. And again, this is an archetype study. We looked at a certain limited number of scenarios. So there are many, many other options and iterations that very smart designers and LCA professionals can consider. This is just trying to give us an initial sense of which arrows are pointing in which directions. So one of the things that we have genuinely heard is that cement can be one of the most expensive parts of concrete, and reducing cement can potentially save costs. And that is what was reflected here in the first 3 bars on the left, or sorry, the baseline in this case was assumed to be not 0% SEMs, but actually the first step in, which was labeled 20% SEMs. So we weren't just using the worst concrete as the baseline, but there was still potential for reductions beyond that and potential cost savings as reported by the costing consultant. Now, we've also, and as the city, I've had detailed conversations with both projects that are working through embodied carbon reductions, as well as actual local concrete and cement manufacturers and suppliers. And my understanding is that if there aren't savings at the initial kind of base levels of reductions in the most typical mixes, you can get some embodied carbon reductions without cost increases. If you go to their lowest concrete mixes, you do actually start to see some cost increases and some potentially notable concrete cost increases, such as up to 10% for the lower or lowest carbon mixes. That's what I've been told is kind of the latest information, but it has been told to me that there are still low carbon concrete mixes available as base mixes that don't have a cost increase over typical. That might be choosing your supplier, that might be tailoring your mixes, but there are still potentially, if not for savings, at least for cost neutrality in terms of reducing embodied carbon in concrete mixes. Some of the other options that we looked at were as a proxy for structural efficiency and using less concrete overall, and also just as a direct option, reducing parking was something we looked at. Whether some product will have the option and the ability to reduce their parking outright, and that can save both cost and embodied carbon because we're just using less material. And as anyone knows, there can be an awful lot of concrete in the foundations and below grade structure. And this can actually be a significant part of costs of construction. So anyway, we're able to reduce parking in below grade structure or reduce overall structure as a matter of designing the structures efficiently can reduce embodied carbon and potentially reduce costs. When we look at the enclosure, there were some other enclosure options that were studied. The baseline in this case was aluminum frame window wall enclosure. And looking at some of the other options out there, and I know window wall is probably the most common that we see in high rise. That's why we chose it as the baseline. But using steel stud frame walls, using sandwich panels with different insulation types, using frame walls with different window to wall ratios potentially. But basically, it's important to understand that different wall types, different ways of building your enclosure and walls in a high rise can potentially reduce the embodied carbon. And in this case, the costing showed it can actually reduce potentially the costs as well. I don't expect that to be the case in all cases. Costs can vary significantly, but it was promising to see that there are potential options to reduce embodied carbon as well as potential to reduce costs. And even if those savings aren't realized, we could at least take that as an indicator of potential cost neutrality. And when I talk about kind of low or no cost options or cost neutrality, these are further supported by another study by the RMI, which I'll touch on at the end. When we put those together, the study looked at a number of different options to reduce embodied carbon by at least 10%. And so we can see a number of kind of different ways of combining reductions. And this in reality is what designers are going to be doing. It's unlikely that any one measure will be the only strategy to reduce embodied carbon in order to achieve the 10% reduction minimums. They'll likely be looking at a whole host of different strategies and combining them in the ways that are most cost effective for your project. And so last but not least, here's the high level takeaways from that RMI costing study called low and no cost ways of reducing embodied carbon. So they looked at a number of different case studies of actual projects that had looked at reducing their embodied carbon and compiled the lessons from those projects. And they basically found that there either no or low cost premium, as in less than 1% cost increment, ways to significantly reduce embodied carbon across a number of different material types. And last but not least, I think there's already been some discussion in the chat about digging in further into going beyond the PathFinder tool and the archetypes to look at further ways or more detailed ways to reduce embodied carbon. And I just wanted to highlight the EC3 tool, which is a free online database of thousands of different EPDs from across North America and across the world. You can zoom in on a specific material and actually look at the different ranges. And it can be very informative to understand, in this case, say looking at the concrete mixes made in BC and their different ranges in carbon intensity. And for those that are familiar with the details of concrete mixes, you can actually tailor it to different strengths, curing times, all kinds of different variables that are important to concrete, and see what low carbon concrete mixes are available. And similarly, you can do it with other major materials. There aren't quite as many EPDs, but say if you go to steel and other major materials, you can see that not only does kind of the amount of material you're using matter, not only does the type of material matter, but also where you're getting it from and the carbon intensity of that specific product that in the end you'll be using. So with that, thank you very much for the chance to present to you today. I look forward to sharing the full report with all of you, and happy to take any questions. Thank you.
So yeah, thank you, Patrick, Ivan, and Navid. Really, really great presentations. There were a lot of questions in the chat, and I know some of our audience members have worked to answer a few of those, but there are some going back right to the beginning. So if you did have a question earlier on that hasn't been answered yet, feel free to unmute yourself and jump right in. Anthony, I know specifically you had 2 or 3. Are you able to jump in there?
Sure. Actually, I think Patrick's answering. Hold on. Sorry, I meant to say the percent cost for. Yeah. That's a percentage of the element you're looking at, right? Not on the total project cost, right?
Yeah. Sorry, I meant to say that the percentages that were shown in terms of change in cost were on the cost of structure and enclosure, not a whole. Not all elements in the building.
But like, I think on the enclosure one, you had like a graph on like the sandwich panel. And I think if I recall correctly, it said something like it was 15% lower on costs, which seemed kind of surprising to me. So that's why I was kind of curious about that.
Fair question. I could always double check.
Yeah, no, it's all good. Let's see, what was the earlier one? Oh yeah, I was just wondering, and Athena may not directly spit this out if you use the assembly builder method, but if Ivan, if you know like what the thickness of those slabs, because I think one of the things is that's where most of the concrete is in those suspended floor slabs. And if you're using that default assumption, and sometimes it's not clear if you can't specify that, but then you're not modeling things like transfer slabs, which can be a huge thickness, like variations and stuff. So that's just something to consider, is it may potentially underestimate on the concrete volume, depending on what the assumption is.
I was going to say, I think for the slabs, we ended up using the built-in assumptions in Athena. So those other things may have been missed as well. But we recognize that there are some shortcomings, and we tried to address some of them, but obviously couldn't really get all of them.
Yeah, but in my experience, that's one of the biggest one, because like that concrete slab thickness is really where all the so that's where the delta could be between that and the other models. And then the other thing is, like, when you're talking about the concrete SCM percentages, just something to note is, like, in the old CRMCA industry average EPD, they oftentimes list ranges, right? So they'll say like, I don't know, 25 to 35% or something. But in reality, what that SCM is actually referring to is the low end of that range. And so when you're actually stating those like 20%, 30%, it's not actually, the 20% is probably a 15%, and just kind of round down by 5. Okay. So that's just something to keep in mind, because they actually do specify it earlier in that EPD where they say, what is the actual assumption? So whenever they're giving a range, they're giving you actually what the conservative end of that number is. But yeah, as somebody else mentioned, there's a new EPD out, so maybe that's a moot point. But anyways, great work.
I think one to think about on the concrete slab thicknesses is that things like tools like Athena, they come in and give you a value that is usually the best case scenario. So it's important to remember that that's something that's achievable. But then when you introduce things like transfer structures within your buildings, that's when the carbon, accelerates. You're adding carbon significantly when you start to introduce transfer structures. So Athena's thickness is probably a great one to start with, but just to remember that people will probably play around with that a bit.
And that's probably why the ranges are on their lower end too, because I think Amy was saying it's like 100 to 400. And when I first looked at those results, I thought they were a bit low too. Like if the max end for concrete high rise is 400, I think it could probably go higher than that, but so the absolute values may change when you do detailed analysis.
Okay, it looks like Harshan has his hand up.
Yeah, thanks a lot for the presentations, everyone. So my question is more of a social science question, if you will, particularly directed at Navid and Ivan as practicing engineers. You folks have clearly kind of developed the expertise to be acting as LCA consultants. But I'm kind of thinking about how do we mainstream the consideration of embodied carbon accounting by folks who aren't LCA consultants to begin with. So I would like to invite you to kind of share your, learning journey about how you develop this expertise so that it can help others to kind of consider, where is that sweet spot if you are a structural engineer or an architect? Do you always have to engage in LCA, or is there a sweet spot there where you could develop enough expertise to kind of address this? So hope that question is clear. I just look forward to your insights.
Yeah, thanks for your question, Harshan. I would say, like any other discipline or practice, you get better at it with experience. So the more project you do LCA and carbon analysis on, get a sense of the impact. So like now, like I think we have done north of 100 embodied carbon analysis in our firm over the past couple of years. So I see a drawing, I get a sense of what the impact could be. But again, like it's important to know that there is a range. So it could be, as Anthony mentioned, that you can have a concrete building that is 250 or 300 kilograms of CO2, and you can have a concrete high-rise that is like 1,000. So it's a wide range, and it comes down to different design choices and different options. So I would say the best way to educate to the public is to look into different like free resources that are out there. Like, I mean, PathFinder is a great example. EC3 that Patrick mentioned is another great tool that lets you dive in at like a more granular level, look at different components of the structure or building envelope, look at different concrete and different EPDs, and like play with those parameters and to see what the impact could be. And tons of online resources available on CLF Vancouver and Zabex that talk about like embodied carbon at different levels, everything from very introductory to very advanced. So I think that those all could be used for people to educate themselves on embodied carbon. I'll pass it over to you, Ivan, if you want to add to it.
Yeah. Just to add to that point, it's embodied carbon and lifecycle analysis is becoming more and more popular, and we're seeing different jurisdictions requiring it or thinking about implementing it. But that's not to say that we all need to be LCA experts, just the same as we do, our energy codes, our energy requirements have been driving building codes a lot, but that doesn't mean we all need to be energy modelers. But there is value in getting some familiarity with it. And as Navid has mentioned, there's many different resources out there. There is this, obviously CLF in general for the bigger organization, CLF Vancouver, Zabex, but also if you're, if you're looking at it from a structural perspective, there's also additional materials from SE 2050 and SEI out there, and they've got a lot of different tools. So I definitely encourage, if you want to get more and learn more about it, definitely come to these webinars, find a local group if you can participate, but also go and do the research in places like CLF, as well as there's also a new LCA guideline from NRC that can also provide some insight. It's just to get yourself out there and get involved. That's the easiest way to learn.
Excellent. Okay, do we have any more questions?
I have a question, Caroline, actually.
Yeah.
Just about, I put a comment in the chat about optimization. A lot of great feedback from everybody attending. And my question is kind of based on the feedback that came out of that question about optimizing your structural design for embodied carbon considerations. Is the PathFinder tool the right place for that? Or does it happen afterwards with a whole building lifecycle assessment tool, like Tally combined with Revit or something like that? Where's the best place for that?
I think, and this is a really good question, I think the PathFinder tool is not the best place for it, just because it's a very simplified set of data, simplified models that you can't make adjustments. For example, if I were to make the slabs a little bit thinner, or change some of the structure so that I can reduce some of the material use, it's not fine-grained enough to allow you to do that. You're only able to compare it between different materials, but it's not getting into too much of the nitty gritty as far as, well, what if I space my columns a little bit further or bunch them a little bit closer together? It doesn't get to that level. So for that, you would need something like a tally or one click or something like that, but also combine it with some expertise from the structural side as well, because you can't just be modeling things that that you can't build with. So you want to make sure that you're within the codes and you still meet all those other requirements.
Adding to that, there's a really great tool that Bureau Happold produced that does optimize building structures for different scenarios. Does things like comparing different grid sizes. For if you're set on a concrete building, say, or set on a steel building, it will compare those options. But what I don't know is, it's what we were kind of talking about in the chat here. As you increase your concrete strength, you need less concrete, and there isn't, I don't know at least, of a resource that tells you what the tipping point is. Whereas the lowest embodied carbon, is it 40 MPa concrete in a certain dimension, or is it 25 MPa concrete in a much bigger dimension? If somebody has a resource that does that, I think that would be a fantastic one to share.
What I would add is that like embodied carbon and like strength of concrete is just one parameter, and there are a few other things to consider, like curing time, like the time that you're pouring concrete. If you're pouring concrete in summertime or shoulder season, you might get like a different strength timeline. So there are different factors that like you need to pay attention to, and as Ivan mentioned, like it's important to not do this type of like embodied carbon analysis in isolation. Have a conversation with your design engineers and like structural engineer, envelope mechanical architecture, to see those different side of it too. Because again, like, I mean, you could get different results based on different timeline or different materials that you're getting, or if you're have a different formwork that you're using on site. So there's so many different factors that can play a role. So it's important not to look at embodied carbon in isolation.
On the note of slabs, Anthony was talking about the slab thickness, which is a really good point. Actually, it's also repetitive, across the entire building. Does the tool include post-tension slabs, which I think can be thinner because they're post-tensioned? Is that an option in the tool?
Hollow core concrete slabs are, but not post-tension.
Okay.
No.
So I would say one of the great things about this, like in addition, yes, it can be helpful for early design. I see one of its greatest strengths as an educational tool. And I can imagine someone on their learning journey about embodied carbon, starting with, I don't know, the World Green Building Council's report, or the materials, Architecture 2040, 2030's materials palette, kind of reading more qualitatively about embodied carbon and what matters. And then they might turn to, and again, this could be a client, this could be anybody, might turn to PathFinder and begin to actually dig in themselves and play with different variables in a quantitative way to see what matters most. And then they might go to other tools.
Point, Patrick, in that that's the high level kind of analysis that this tool is capable of. So I like that point.
Okay, great. I've just done a quick scroll through the chat here, and I don't think if we have missed a question, I'm not seeing it right now. So last opportunities for questions before we end for the day. Okay, great. Thank you very much again to all three of our speakers, Ivan, Patrick, and Navid, and thank you to everybody for attending today. I think this was a really great conversation. This recording will be posted on our YouTube channel in the next few days, and we'll also post a link to the slides as well as soon as they're available. We will have another webinar next month, and we are also planning to have a social event next month, so save the date for October 12th for anyone in Vancouver, and we'll send out some more information in our newsletter. In the meantime, enjoy the weekend. I'll see you all soon.